This is Physics 2110, Lecture 31. Today we're going to start talking about diffraction patterns. So light that has a wavelength comparable to or larger than a width of a slit spreads out in all forward directions upon passing through the slit. This phenomena is called diffraction. It indicates that light spreads beyond the narrow path defined by a slit into regions that would normally be in shadow if light always traveled in straight lines. A single slit placed between a distant light source and a screen produces a diffraction pattern. It will have a broad, intense central band called the central maximum. The central band will be flanked by a series of narrower, less intense secondary bands called side maxima or secondary maxima. The central band will also be flanked by a series of dark bands called minima. So the diffraction pattern consists of a central maximum and a series of maxima and minima. The pattern is similar to an interference pattern. This shows the upper half of the diffraction pattern formed by light from a single source passing by the edge of an opaque object. The diffraction pattern is vertical with the center maximum at the bottom. A Fraunhofer diffraction pattern occurs when the rays leave the diffracting object in parallel directions. So if you have a screen very far from the slit, or we could put a converging lens in between the slit and the screen. The bright fringe is seen along the axis at theta equals 0. Then we have alternating bright and dark fringes on either side. So this shows light coming through a slit, and as it comes through the slit, I get the broad central maxima and the secondary maxima that are going down in intensity. So diffraction refers to the general behavior of waves spreading out as they pass through a slit. A diffraction pattern is actually a misnomer that's deeply entrenched. The pattern seen on the screen is actually another interference pattern. The interference is between parts of the incident light illuminating different regions of the slit. So, the finite width of slits is the basis for understanding Fraunhofer diffraction. According to Huygens' principle, each portion of the slit acts as a source of light waves. Therefore, light from one part of the slit is going to interfere with light from another part of the slit. The resultant light intensity on a viewing screen depends on the direction theta. The diffraction pattern is actually an interference pattern. The different sources of light are the different portions of the single slit. All the waves that originate at the slit are in phase. So wave 1 travels farther than wave 3 by an amount equal to the path difference, which is a over 2 sine theta. If this path difference is exactly half of a wavelength, the two waves cancel each other out and destructive interference results. So in general, destructive interference occurs from a single slit when the width A, when sine of theta dark, so that's where the destructive interference occurs, is equal to m lambda over A, where m can be plus or minus 1, 2, and 3. So let's look at an example. Light from a wavelength 580 nanometers is incident on a slit having a width of 0.3 millimeters. The viewing screen is 2 meters from the slit. Find the positions of the first dark fringes and the width of the central maximum. So we know sine theta dark, and the sine is approximately y over L, is equal to plus or minus m lambda over A. Well, for the central maximum, it'll be the first one, so m is equal to 1. So solving for y is equal to plus or minus L lambda over A, and plugging in our values given, we get plus or minus 3.87 times 10 to the minus 3 meters. So the distance then between the two maxima, so if I have a screen here and I look and I've got the central maximum. So if this is 0, this is minus 3.87 times 10 to the minus 3. This is plus 3.87 times 10 to the minus 3 is where our dark bands occur. And the width of that then is twice y, which is 7.74 millimeters. The general features of intensity distribution are shown here. We have this broad central fringe is flanked by much weaker bright fringes alternating with dark fringes. Each bright fringe peak lies approximately halfway between the dark fringes. The central bright maximum is twice as wide as the secondary maximum. We can use phasors to determine the light intensity diffraction for a single slit diffraction pattern. The slit width A can be thought of as being divided into zones, each zone having a width delta y. Each zone is going to act as a source of coherent radiation. The path difference between here is delta y sine theta. So each zone contributes an incremental electric field delta E at some point on the screen. The total electric field is found by summing the contributions from each zone. The incremental fields between adjacent zones are out of phase with each other by amount delta beta, where delta beta is 2 pi over lambda delta y sine theta. So at theta equals 0, all phasors are aligned, and the field at the center is just n times delta E, which is the total intensity of that light. So the resultant phasor is at a maximum. Now, for a small angle, each phasor differs in phase from the adjacent one by the amount delta beta. And so ER is the vector sum of the incremental magnitudes, where ER is less than the original light intensity. The total phase difference, then, is however many zones I have times delta B. So it's going to be 2 pi over lambda A sine theta. Now, as theta increases, the chain of phasors eventually is going to form a closed path. The vector sum is 0, so ER is 0. This is going to correspond to a minimum on the screen when beta is equal to 2 pi. At this point, theta is 2 pi is in delta beta, so therefore sine theta dark is lambda over A. And remember, A is in delta y. It's the width of the slit. So that's the first minimum, which is what we had before. At larger values of theta, the spiral chain of the phasors tightened, and then we get a secondary maximum when beta is equal to 360 plus 180 degrees, or 3 pi radians. So the second minimum is going to occur when this completes the circle, and I have ER is 0 again. That's going to appear at 4 pi radians. So we can consider the limiting condition as delta y gets infinitesimally small, and we'll call it the infinitesimal dy, and n goes to infinity. Then that phasor chain becomes a curve. The length of the curve, or the arc length, is E naught. The chord length is ER. And from a little bit of geometry, we know that sine of beta over 2 is equal to ER over 2 divided by the radius. So the light intensity at a point on the screen is proportional to the square of the electric field. I is equal to I max times the square of sine of beta over 2 divided by beta over 2. I max is the intensity at theta equals 0, or the intensity of the central maximum. Then putting in what we have for beta, I is equal to I max times the square of sine of pi a sine theta over lambda divided by pi a sine theta over lambda. The minima then are going to occur when pi a sine theta over lambda is some integer number of pi, or when sine theta is m lambda over a. So most of the light intensity is concentrated at the central maximum. And the graph here shows the light intensity versus angle. Now what happens when I have two narrow slits? So when more than one slit is present, we have to consider the diffraction patterns due to the individual slits and the interference due to the wave coming from different slits. So the single slit diffraction pattern acts as an envelope for the two slit interference pattern. So let's consider our problem. Find the ratio of the first two secondary maxima to the central maxima for a single slit Fraunhofer diffraction pattern. So, for the first one, I is equal to I max, but we're comparing to I max. So I over I max is the square of sine of 3 pi over 2 over 3 pi over 2. To work that out is 4.5%. So the first secondary maxima is 4.5% as intense as the original one, as the center maximum. And for the second one, now it's sine of 5 pi over 2 over 5 pi over 2 squared. We work that out, it kind of turns out to be 1.6%. So it goes down from 100% in the central maximum to only 4.5% of that, down to 1.6% for the third maximum. To determine the maximum intensity of a two-slit diffraction pattern, then, I is equal to I max cosine pi d sine theta over lambda, that's what we had last time, times this single slit diffraction pattern. It's going to act as an envelope for the intensity. So the two-slit interference term is the cosine squared term, and this is the diffraction part due to them being very narrow slits. So if we look at an interference pattern for two small slit device, and perhaps you saw this in your lab, you see the evenly spaced bright and dark fringes from a two-slit diffraction pattern, but the overall intensity is governed by the single slit envelope. And so I get a bright central maximum, and I get a secondary maximum, and so I get that each of these interference pattern ones are getting brighter and darker based on the single slit diffraction pattern. So to find maybe which interference minimum or which interference maximum coincides with the first diffraction minimum, or the missing orders, it's going to happen when d sine theta over a sine theta is equal to m lambda over lambda, or d over a is equal to an integer. So the conditions for first interference maximum is d sine theta is equal to m lambda. The condition for first diffraction minimum is a sine theta over lambda. The next thing we want to talk about is resolution. It's the ability of an optical instrument to distinguish between two closely spaced objects, and it's limited because of the wave nature of light. If two sources are far enough apart to keep their central maxima from overlapping, the images can be distinguished, and they're said to be resolved. If the two sources are close together, the two central maxima overlap, and the images are not resolved. So here, if I'm looking through these two objects through a slit, if the images are far enough apart, that is, the light coming through them, the central maximum do not overlap at all, then they are just able to be resolved. The angle subtended by the sources at the slit is large enough for the diffraction patterns to be distinguishable. If the sources are so close that their central maximums do overlap, then the angle subtended by the sources is small and the diffraction patterns overlap, and I can't see them as two different objects. The images are not resolved. So when the central maximum of one image falls on the first minimum of the other, the images are said to be just resolved, and that limiting condition of resolution is called Raleigh's criterion. The angle of separation, theta minimum, is the angle subtended by the sources for which the images are just revolved. Since the wavelength is much, much smaller than the aperture size in most situations, sine theta is very small, and sine theta is a lot bigger than theta. So instead of sine theta, I can just use its approximate equal to theta. Therefore, the limiting angle in radians of resolution for a slit of width A, theta minimum, is lambda over A. So to be resolved, the angle subtended by the two sources must be greater than theta minimum. The diffraction pattern of a circular aperture is going to consist of a central bright disk surrounded by progressively bright and dark rings. The limiting angle of resolution for a circular aperture, theta minimum, is 1.22 lambda over d. That's the diameter of the aperture. So for example, if I'm looking at something under a microscope or through a telescope, if the sources are far apart, the images are well resolved. The solid curves are the individual diffraction patterns. The dashed lines are the resultant of what we see. So we see two objects followed by the patterns of bright and dark. Here the sources are separated by an angle that exactly satisfies Rayleigh's criterion. So the images are just resolved. So the central maximum occurs on the first minimum of the other. So I can see here that there are two different objects. I can't really distinguish them, but they are still said to be resolved. Now here the sources are close together. The images are unresolved, and so what I see when I look through the aperture, I can't tell that there's two objects. It looks like one single object. So, for example, if I were looking through a telescope, here we are looking at Pluto and its moon Charon. On the left is an Earth-based telescope, and it's blurred. I really can't see that there's two objects. The telescope's diameter is a little bit smaller, and so I don't have enough resolving power to see there's two different objects. However, if I look at this with the Hubble Space Telescope, I clearly see that there are two different objects. So let's look at a microscope now. Light of wavelength 589 nanometers is used to view an object under a microscope. If the aperture of the objective has a diameter of 0.9 centimeters, what's the limiting angle of resolution? And then, if the object is 1 centimeter from the objective is 1 centimeter from the object under the telescope, what is the size of the smallest object that can be resolved? So, for the first part, we use Raleigh's criterion. Theta minimum is 1.22 lambda over d. We plug in our wavelength. We plug in the diameter of our objective lens. We get 3 times 10 to the minus 5 radians. Now, if the objective is 1 centimeter from the object, then what is the smallest size? Well, d is going to be 0.01, 1 centimeter, times the resolving angle. We get 3 times 10 to the minus 7, or 0.3 micrometers is the smallest object that we can resolve with the microscope. So what's the resolving power of our eyes? What is the limiting angle of resolution for the human eye, assuming it's limited by diffraction? So let's use a wavelength of 500 nanometers. And we're going to use a pupil size of 2 millimeters, which is the average daytime size of your eye pupil. So theta minimum is 1.22 lambda over d. So we get 3 times 10 to the minus 4 radians, or essentially a minute of arc. If this is at the near point of the eye, which we said for an average person is 25 centimeters, the smallest object that can be resolved, d, is 8 times 10 to the minus 3 centimeters. So anything smaller than that at your near point, you won't be able to resolve. What about the resolution of a telescope? The Keck telescope at Mauna Kea, Hawaii, has an effective diameter of 10 meters. What's the limiting resolution for 600 nanometer light? So we plug in Raleigh's criterion, 1.22 lambda over d. Lambda is 6 times 10 to the minus 7 meters. The diameter we said is 10 meters. So it's 7.3 times 10 to the minus 8 radians, or 0.015 seconds of arc. So it can resolve two objects that are very, very close together. So, to review what we talked about today, we talked about diffraction and how with a single slit, light from different parts of the slit interfere with each other and form a diffraction pattern. We talked about single slit diffraction patterns, or Fraunhofer diffraction patterns, and how they act as an envelope around a two-slit diffraction pattern. And to end, we talked about resolution and resolving power of different optical instruments.